Leetcode 211, design, add and search words data structure. Yeah, so there's a data structure that we will have to design, quote unquote, which will be used for adding and searching for words. And on the right side, I will have already provided on the public interfaces, at least the class is called word dictionary, and we have two public methods, add words and search. Yeah, that's why add and search. And we have to figure out the backend here, so the things which will happen behind those functions, or what will happen when we call those functions, and they will operate within a single class. And we'll have to figure out how to do it in the most efficient way, but also not too complicated, since such questions are usually given during job interviews, and then you have at most half an hour, maybe even 20 minutes to figure everything out, also to explain and to code. Yeah, so it cannot be overly complicated, but still has to be efficient. And I said quote unquote design because most of the design is already done, and we will have to just fill the blanks, which is still a lot of work. And let's just keep reading. Design a data structure that supports adding new words and finding if a string matches any previously added string. So it's basically a try. If you don't know what a try is, it's a special type of tree. But if you haven't yet implemented a bare try or a row try, where you don't have anything additional to the this most basic functionality of a try, if you haven't implemented it yet, then definitely do it beforehand, because this will be basic regex added on top of the try implementation. So that's a spoiler already here. And the hint for using tries is, of course, adding and searching for words. Yeah, tries are very efficient for search on strings, and basically whenever you have to implement some data structure, or maybe some class where you have to do something with word search, then most of the cases you will have to use a try, and sometimes it will be already provided for you. You will just have to modify it slightly, or maybe just use the ready try, and in this case we'll have to implement it from scratch, and that's what we will do. And the next thing, which I haven't mentioned yet, is this medium, which I would say is a bit of stretch. Yeah, that's a little bit too much for medium, and definitely it's like an entry-level hard, or like a very, very hard medium, if there is such a thing. Yeah, so compared to other mediums, it's definitely harder. And let's keep on reading. Implement the word dictionary class. That's what we said. This class, which is already provided for us here on the right side, which will have, of course, a constructor or init method, as they call it in Python, which initializes the object. And then those two public methods, one for adding words to the data structure. It can be matched later, so we will have to have some kind of memory, and the words that are added have to be stored somehow. And of course we'll use tries for this. And search returns true if there is any string in the data structure that matches word, or false otherwise. Word may contain dots. Yeah, so this is this additional stuff to bare tries. Yeah, so there's like basic regex on top where dots can be matched with any letter. And of course there are like multiple questions and problems on Leetcode and or other algorithmic on other websites with algorithmic programming and problems, and this is like the most basic one when it comes to this class of problems connected to regex. Yeah, so this is the whole class, as I said, of problems when you can have different regular expressions that you have to implement yourself. Yeah, so if it's also something new for you, then I'm just trying to highlight that it's something that also reappears quite commonly during job interviews, and you should definitely study how to, first of all, what kind of regexes exists, yeah, how to use those already implemented, and then think about how you can implement them on your own, since it's like a very common pattern that like here you will have just a very small part of regex that you will have to implement within the problem. And in this case, we of course have to just implement dots, which can match any letter, but they have to match a letter. So for example, stars can match, but doesn't have to. Can also mean something that is empty, like no char at all. But dot means that it has to be a letter, and it has to be a single letter, which is of course much easier. And still, it's much easier than it could be otherwise, but still something that is not extremely straightforward, and you have to think about it for some time to get used to it. And that's more or less it. So that's the whole task. Now let's take a look at examples. And we have just one example here, which looks like this. Those strings in the first array basically represents the operations and the methods that will be called from our class. So first of all, they will create an object of that class, and the second array represents the arguments that will be passed to those methods. So for initializing the object, there is nothing here because we just take self and nothing else in it. Then we call add words 3 times. We add bet, dat, and med, and then we search for pet. And of course we haven't add pet yet, so this will return false. But then we search for add with dot in front, and this have to return true because it matches actually all 3 of them which have been added. Then we use b with 2 dots after, and this is also true because we have bet, for example, that matches it, and that's it. So that's the whole example. So 3 times true and single false for pet. And now we have to think about how to implement that interface, and we will do it here. So I already revealed part of the answer before. We can just, by the way, concentrate on those 2, since nothing especially interesting will happen in the init. We will just create a root object for our root node in our try. So as I said, we'll use tries, and on top of that, the second spoiler will use DFS for iterating or going over all possibilities when it comes to dots. So we will have to figure out a way in order to search for those possible matches when it comes to dots, and we will do it using old good DFS. And let me just copy this as well, and let's think about the details. But first, let's write down what we have already mentioned, meaning that we'll use tries, implement try, and node class will store. So the try will be created by coupling together or connecting together objects of a node class. So we'll not have a class for the whole try. We'll just have nodes of the try, and of course try is a type of tree. Tree consists of nodes, and we'll have a class that will represent a single node. A single node will store a single character and references to the children, which will store single character and references to the children. And one more thing, we'll have to also mark the end of the word to separate the termination characters from normal characters, and mark word ends. Like this. So that's what we will do for tries. And the second thing, so basically in this first method, we'll just use very standard try implementation. We'll be adding new nodes to our try, which will be objects of this new class, this brand new class that we'll design and implement in a second. And for search, we will use also normal search, which goes through each character of the word and then tries to match them with existing nodes. But in a case of a dot, then we will use this DFS search to extend this row implementation, which with additional stuff that we need for this particular program. And let's try to write it down. I already forgot half of the things that I said, but for search, we will use DFS. And in a minute, we can also discuss why DFS and why it is a search problem. Yeah, like already search is a hint that we will traverse through some data structure. In this case, of course, we will traverse through data structure because this search is for our new class, for our new data structure that we are designing. And traversing through a data structure or searching through data structure are two different terms for basically the same thing. And since trees are graphs, those are like as they belong to graphs as well, we can use DFS and BFS for traversal. Yeah, and in case of both DFS and BFS, each of them has their own specific use cases and their own advantages and disadvantages, and I don't want to go very deep into differences between them, since I'm repeating this a lot, since it's very common thing. Basically, in any medium to hard problem, you will find you have a very high possibility that you will use either DFS or BFS. And sometimes there is a clear advantage. In this case, you could use both of them, but DFS, I think, is more natural. And as we will discuss deeper what we will do in the search, I will highlight it more. But right now, I just want to say that you could use BFS as well, and they would have exactly same time complexity, or you could implement it in a way. Of course, you can implement it in some convoluted way, which will have worse time complexity, but theoretically you can implement both of them here, and they would end up having same time complexity. But I still think that practically DFS would be faster and easier to write, and that's why I'm choosing DFS. And there is one more advantage that I will explain when we will go deeper into implementation of this method. Yeah, so for search we will use DFS, and for normal characters, or for letters, since we will have either letters or dots, and for letters we will use row try search, and only if we encounter this a dot, and then we will bring our heavy gun DFS. We'll use DFS. So maybe like this. For search, we have two options. And tap, tap, and tap. And this we can do like this. So we have two cases for search, either normal letter, and in this case we use just row try search. So just iterating in a loop over letters and trying to match them with existing nodes. And if we encounter a dot, then we will have to go over all possible children. Since if it's a normal letter, we already can decide does the child exist or not. If it's a dot, then we have to go over all children, since we don't know which exactly it is, or we know that all of them are a possible match, and that's why we have to do something more advanced than for normal letters, and that's more or less the whole philosophy. So row try plus this DFS to just to handle the special case of dots. That's it. So now let's discuss add word and search, but maybe before let's move it below. Let's try to do some visual example. Let's say that we have following words: bed, bag, band, and bank and band. Like this. Yeah, and in our try we'll have a root which doesn't hold any letter, and then from the root we'll have a single child, letter A, not letter A, letter B, since all of them start with letter B. Now, the try stores a single character and references to the children, and those references are represented here by arrows. And then B has also a single child, and that's A. Then A has 3 children. D, G, and N. D, G, and N. Yeah, and D and G are terminal characters. Yeah, the word ends here, meaning we have to mark it somehow. Let's mark it by an additional asterisk, like this, and N. Let's move it to the bottom a bit, and N has two children as well. And this is what will happen once we call add word function. We will build this tree using those node tries. And we'll have K here and D as well. And those two are also terminal characters, K and D. And now let's say we want to match. We search for BA and then 2 dots. How will we proceed? So we start from the root. We check if B is one of the children of the root. We use normal row try search. It is. So we go here, then we have A. We check if A is one of the children of B. It is. We go here. And then we have to explore all the possible options. We go here, here, and here. Yeah, and we don't explore them like this. We go first to one child and try to go as deep as possible. That's the DFS. And of course, if we go to those children in this order, then we will try to go to D and try to check if D has any additional child. No, it doesn't. That's why it's a wrong. It was a wrong choice. We don't have as many characters as we want. And at this point, we terminate and we do what? We backtrack. DFS uses backtracking, another important term. And the same thing happens for G. We go to G, it matches the first dot, but there is nothing for the second dot. We also terminate and we backtrack. Then we go to N. And for N, we have K, which is already okay. We have two possible options. And that's it. At this point, we return true because we just want to have a single match. We don't return the matched words, we just return true or false. And maybe that's why it's a medium and not hard problem. But either way, you have to understand all of this, how it works to implement it. Yeah, and if we, for example, had something like this, okay, then we would do almost exactly the same for this particular tree, just that if we went for D first, then we would have to backtrack and try K second, and in the end return true. Yeah? And if there was something which doesn't exist like this, then we would go to this dot and try all possible options, and all possible options are only for A, since we have just one child on this position, and then this child doesn't have any child which would match Z. So those this is more or less how it works. So just normal iteration through letters for letters, and for the dot we do almost the same, just we have to explore all the possibilities, but by going as deep as possible into the first one that we try. So here we can use try nodes, and for them we will use default dicts. We can use normal dicts, but default dicts make it a little bit easier, since if a character doesn't exist, or a node in our case doesn't exist, they will create them by default. And we don't have to do any if else. And start from the root. We'll create a root node in the init function in our constructor and add character by character. And that's it. It's very simple how to implement add word for try. Yeah, just a single loop. And for search, we also start from the root, and we keep track of the length. And then we will have recursive DFS. And inside this recursive DFS, we have multiple cases, at least three. And the first case is the base case, where we terminate with success if current index is, so keep track of maybe the indices and the total work. Yeah. So 0 will be and root will be our first node, and 0 will be our first index, and we'll try to go character by character, and with each character we'll increment the index. And if the index number matches the total length, that means, and we haven't terminated with failure before, that means that we can terminate with success. Equals the total length. That's the first case. Should be easy, and like this success for us. Thank you, autocorrect, which, by the way, probably also uses tries. Then we will have recursive case, which of course consists again of at least two cases. First case we have a dot on current index, and we have to try not like this, not type of tree called try, but try like in the word trying, or an attempt. We have to try to call DFS. Yeah, it's a recursive DFS on all the children of the current node. And so those are the two cases. And the third case, which again consists of two subcases, will be this normal row try search, which goes through letters. So check if there is a child of previous node of the previous which matches the current letter. And if not, then we can return false already. We can terminate at this point. If yes, we continue recursive calls. If no, terminate with failure. And if yes, continue recursive DFS. That's how you spell recursive. Okay. So that something is here. Some letter is doubled, but looks like not. And that's it. So that's like high-level overview, and the implementation we will go one by one with all of this. But first we have to implement the tries. So let's create our node class, and from collections import default dict, which is a little bit easier in this case to work with. The normal dict, since we can avoid couple if-else statements, and self children will be default dict of what? Of nodes. Yeah. And where are the letters here? The letters will be the keys. And we will have also a marker for terminal characters. If it's end of the word, we will store true here, but by default we store false. And here in the init method in our constructor, we just create root object with no children yet. And that's it. And now to add a word, we will start from the root. First node will be root. And then for each character, we either have already this corresponding node created, or we have to create it. Okay, so two options. Either it already exists, a node that matches that character, or it doesn't. And in this case, in both cases, we just do the following: node.children at the position of that character. Yeah. So default dict takes care of both cases. Yeah. If it doesn't exist, it will create a new node. If it already exists, it simply returns it. And that's it. That's how we add characters. And for search, we will have to use this iterative DFS. and we will need an index as well as current character. And by the end, we'll call it, so we'll implement it inside the search function. It will be like private function inside, and we'll call it starting from index 0 and from the node root. So maybe not character, just node. We will be updating the nodes, and characters we can get by accessing character equals word on position index. But first of all, we can handle our base case. If index is equal to length of the node, that means that we have reached positive, not length of the word, length of the word, not of the node. That means that we have reached the positive end, success. We have updated the index as many times and finding matches all the time, meaning that we are already done with this problem and we can return true. Otherwise, we have to handle the case of character being a dot. And here we will have to go through for nodes children through each possible child like this, and call DFS on each of them by incrementing index by 1 and passing child as a new node. And if it returns true, any of them, then we can return true. If none of them returns true, then we have to return false already. That means that we haven't found any match for this dot. And otherwise, now we are in this third case, which again has two subcases. It's a normal letter, and we can have child. We can access child like this node. And now we will use get, yget, and not curly braces, square braces, because this creates a new node if there is no such node. If there is no node which is matches or corresponds to our character, and get will not create a new node. And we want to distinguish between nodes which are invalid and which are valid. And that's why we use get instead of square brackets. And now we can return DFS on index +1 for the child if child is not none, else we return false. So here are those two subcases. That's it. Now let's try to run and see if it works. For the first case, it worked without problems. Now let's test it on all the cases and see. We failed on some cases, and that's because we haven't used end yet. So I created it, but then I forgot to use it in practice. And here we have to mark end of the word like this, true. And here we don't always return true. We only return true if it's the end of if we have reached end of a valid word. And because we could have, for example, just two dots, but there is no two-character word in our dictionary, and in this case we'll have to return false. So let's run just for the first case as a sanity check. And now all the cases. And we are faster than 85% of other competitors. Okay, before we go, let's quickly discuss time complexity and space complexity. And time complexity here is O of L or O of N, however you want to call it, where this character, this letter L or N, is the length of the input because we have a single loop. And if we assume that under the hood, this default dict works with O1 for insertion and returning, which it should. And so if this itself is optimal, how it's implemented in Python, and it works with O1 and time complexity, then overall here time complexity is OL or ON, and depending what kind of letter you choose to represent the number of characters in the word, since we are iterating through each of them in that loop. And here we also have a loop, not here, but yeah, this will be our loop since we go index by index. Yeah, or if there is not a single dot inside, then it's also OL. Yeah, and if this extraction costs O1, yeah, then which I assume it does, and we don't have any dots, then we will do it just L times. Yeah, for each character we at maximum we will do it once. We can do it less than the number of characters if we find an early mismatch. Yeah, and this thing complicates stuff a bit. So in total, the number of children here can be maximum 26, yeah? And the number of dots can be k. Yeah, so if the number of words, if the number of letters in the words is L, and the number of dots inside this word is k, yeah, then the total complexity will be 26 to the kth power times L, because at each dot we have a new divergence and new possibilities which multiply with each other. And so it's not an addition, it's a multiplication. That's why it's to the kth power, and k is less than or equal to L. Yeah, of course, you cannot have more dots than all characters in the word. And that's more or less it. But I think there was some additional constraint for that. Yeah, that there will be at most 2 dots. Yeah, so in our case, k is equal to 2. So it will be 26 to the second power times L. And that's it. So that's the discussion about time complexity.